This is an introduction to Mach 3 Turn. First of all, I'd like to thank Steve Blackmore for designing these screens. Myself and Steve talked about this at great length. Steve's a minimalist and believes that the fewer controls on a screen, the better it is in terms of accuracy for a lathe user. He's 100% correct in this. The mill screens are a lot more complex than the turn screens, primarily because there's a lot more ways you can do something and still maintain accuracy in mill operations. As a result, Mach 3's turn screens are very simple. There are only about 5 screens for you to look at and to use, and one of those is diagnostics, which you won't use much. This is the selector screen and is the screen that you will come up with in the program when you first start it up. Down here we can see there's a diagnostic screen. Just as the diagnostic screen in mill is primarily designed for myself to provide support to users that are having problems, the same is true here in turn. Most of the things on this screen you will not need to use or to look at in common operations. There are times, however, if you're having difficulties, that I may ask you to check something on one of these screens just so I can get a better idea of what exactly your problem might be. If we start here by looking at the manual screen, this is where you'll set up your job. You won't typically load a program while on this screen, and as you can see, there is no button on the screen other than in the main menus that never change in order to allow you to load a G-code program. This is because we really don't want you to load G-code programs in this screen. This screen is meant for setting up and adjusting your lathe's position to match up with your coordinate positions that are displayed here. You can see there are only 2 DROs. It is possible to add more, but it is difficult as well. If you're going to use a tool changer, it's best to use the tool screen to simply drop an extra DRO on while you debug macros that are used to drive a tool turret. But again, that's an advanced thing, and we won't get into that. At the moment, we'll assume that you're using just your standard 2-axis lathe. You have an X and a Z. And you can see here on this screen, I can jog and move around. And what would be typical here in terms of workflow is that you put a piece of stock into your lathe spindle. You drive in. On the Z, you would position your tool into the correct position to take a skim cut. You would jog yourself in and take a skim cut on your material. At that point, you'd measure the diameter. In this case, we're in diameter mode. So you'd measure the diameter of the piece that you just skimmed without moving your tool away. And let's say that that is 14 millimeters in diameter. So we would enter 14 millimeters into the XDRO, saying this is the true measurement of the piece that I'm doing. Now, the Z location depends a lot on the G-code program that you've generated. Some G-codes would be posted as beginning from Z0. Others would be generated as beginning from a particular spot on the Z axis. This is something you will normally know where you're going to be beginning, dependent on the G-code program that you're using. We're going to assume, for the sake of argument, that we're going to be starting at a Z of 0. This means that the tip of your tool, where it's resting right now, is a Z of 0. By hitting part 0, we just set our DROs to indicate to the program that we're currently at plus 14 and 0. And this will match up with the part that you have. From that point, you could jog away and go wherever you want. When you start your program, it is at least going to be accurate in terms of the coordinate positions. There's 2 coordinate positions in turn. We use G54 for a forward tool post. We use G55 for a rear tool post. Having 2 coordinate positions, one for the front tool post and one for the rear, allow for some more efficient operations of dual tool post systems. Most of you, however, are only going to be using one tool and with a forward tool post. The program is set up to do more advanced operations, however, and this is why we have multiple coordinate systems. You needn't worry about that at the moment. Most of the time, you're going to be in program coordinates. Machine coordinates are available to you, but unless you're using home switches and you understand the various offset systems, you would normally leave it on program coordinates. The machine coordinates button can be handy for debugging or wrapping your mind around the concepts involved. We won't go there, though, at the moment. The 0 World X and 0 World Z buttons clear your machine coordinates, as well as your offset work offset systems. Be careful with these buttons if you use home switches. If you don't use home switches, these are a good way of simply clearing out all your offsets because you want to start from scratch. This happens a lot for people who are just beginning with Mach 3 turn. The rest of the buttons on the screen are fairly self-explanatory. We have a slow jog percentage, and the plus and minus arrows will increase or decrease that percentage by 5% each time you press them. Your feed that you've set your machine to is a smart DRO, unlike MIL. In this, you select your forward and backward arrows or simply type in a value to be used as a feed rate. This display changes whenever an axis is moving. As you can see, when I jog my Z-axis, I'm now displaying 65.3 millimeters per minute. When I release the button, it goes back to displaying what the requested feed rate is for a G-code move. The increments for the plus and minus buttons are selected here under the F increment button, and the spindle is much the same. You can type in a spindle speed, or you can use the up and down arrows to increment that spindle speed. This display here, S true, will display the actual spindle speed, and this is received from the index input signal. We use a 1 pulse per revolution index signal. This is often done with the Omron SB5V optical sensor with a piece of reflective tape. Some people have optical sensors that go through a single hole in a slotted wheel on their spindle. Either way you look at it, as long as you feed it 1 pulse per revolution, you'll get an accurate spindle speed reading. There are alternatives to that where you can feed up to 12 or 15 or 16 pulses per revolution, but we found through testing that really all that's required is 1 pulse per revolution system. Here we have our jog cycle increments in case you're going to be jogging in step mode. These work the same as in MIL. Down here you'll see a tool number. This is mainly used simply as a display so that you can see which tool that you're currently using. In turn, most of your tool switching will not be done through DROs. You will simply type a command T0101 for tool 1 offset 1, and as you can see the tool number will update. The LEDs are simple. We have jog is on and allowed at the moment. You can see here that you can turn off the capability of jog in case you set up your machine and you want to make sure that you don't make a mistake by pressing a key on the keyboard and thus throwing yourself out of a coordinated system. We have reference lights to show whether or not we have homed our machine. Mach 3's options do allow for these homed lights to be left on, and if you don't have home switches, pressing home at any time will home you on the spot, and the system will then zero itself to that position. The Part 0 button, as I've said, is simply for setting the location of where you currently are. As you can see, I just pressed it, but nothing happened because we're in machine coordinates. If we go to program coordinates, you'll see that it does lock us into the proper coordinates. Entering any numbers into these DROs and hitting Part 0 will shift the current work offset system, front or rear tool post, to a displayed DRO setting which calibrates your machine to that position. So whenever you use these, you should make sure that your axis is in a position that you know is a calibrated position. And the best way to do that is to take a skim of material off, measure the diameter of the material, enter it in, and hit Part 0. You're now calibrated. That's pretty much it for the manual screen. Basically, its use is simply this operation here where you will go in and calibrate your machine to position. After that, you'll exit this screen and enter the auto screen. The auto screen looks very much like the manual screen, and it has pretty much the same reason for existence. In fact, I rarely use the manual screen. I tend to use this screen. I can zero my parts here just as well as I can on the manual screen. But here I can also load files and unload files. You don't run a program from this screen. This cycle button down here takes you to the cycle screen, which is where you actually run your lathe program. Here, you will mainly load G-code programs. And as you can see, I just loaded a threading routine. Now this threading routine, you can see this long red line. It's because I've zeroed my position to be accurate to the lathe, but I'm way away from where this G-code program starts from. So whenever you're zeroing, especially the Z position, of your machine, you should make sure that the Z that you're using is the starting point of your program, or at least is close to the starting point of your program, and you're comfortable that that's a good starting spot to run that program from. That's something that you'll learn through experience as you begin to go. The toolpath display, these 3D shaded objects try their best to show you what your stock's going to look like. They're not always perfect, and not a great deal of time has been spent in making them completely accurate to the true world. They're really just a quick indicator of what you're doing. And in this particular case, we're doing a threading job, and if we zoom in, you can see parts of the cylinder will disappear when you clip them off the screen. You'll see your cutting job, and this is a standard thread. Holding down your right-hand mouse button will pan the object around the screen, and holding down your right-hand mouse button will zoom if you go up and down, and going left to right will rotate the job slightly so that you can see it perhaps from a different angle. Also on this screen is an MDI line. MDI lines are very handy in turn because there's often times where you wish to do something to clear your material or to prepare yourself for a job. As you've seen earlier, we zeroed ourselves to 14 and plus 5 wherever our tool is sitting at the moment. And before you start the job, for example, you may wish to move that X a little bit away from your material so that you can begin your job. We can unload a file, load recent files, or load standard files. We can turn on a spindle or coolant from this screen, or we can stop a running job. The stop is here more just in case you've flicked back to this screen while you're running a job. You want to have a stop button available without having to necessarily press the reset button. If we hit the cycle button, it takes us to our actual screen that you would normally use for running a job. Now in this screen, you do have a G-code display, and you can see this is a very short program. Most of the blue area here, which is doing the cutting, is in this one line, G76, which is a threading macro. And all the terms that come off of this G76 instructed on what pitch to make the thread, etc., etc. Those will be in the documentation to show you how to select those things, but there is also a simple threading wizard which will allow you to design a thread and write this program. I believe this program was written with a wizard, in fact. Though I could be wrong, and it could be one of Steve Blackmore's threading programs. We have displayed up here the X limits of our program. These displays look at our program overall and decide what is the furthest distance out we will come from the center of axis, and how close will we get to the center of axis. Same thing here with the Z. It will tell us how far away we will how far to the right and how far to the left we will end up going during this program's run on the Z-axis. We have indicator lights to show us if we're in constant velocity mode, something you normally are in turn. Whether or not feedback is enabled in the software. The feedback being enabled tells us that the software will be looking for a spindle index pulse and will be using this spindle speed to control various things in the program, such as threading, synchronization, as well as constant surface speed. This DRO down here is the constant surface speed. And what you see here is, if you are in metric, an indicator of the number of linear meters of material that you're going to strip from your material per minute. If you're in standard mode and using inches as your measurement, this would indicate the number of feet per minute that you're going to take from the material. And if we go back one step to our manual screen, you'll see as I jog further away from the center of rotation, X is now increasing, which means we're going away from the center. My constant surface speed indicator is also increasing, because obviously the closer we get to the center as this object is spinning, the less material we will be taking off per minute at a given spindle speed. The further we get out from the center of rotation, the more linear meters per minute or linear feet per minute of material that we would be removing. Although this is displayed at all times, the CSS LED tells you whether or not you are in constant surface speed mode. To go to constant surface speed mode, you need to use the appropriate G codes, G96 and G95, to switch between the two to select a CSS mode. In CSS, your axis movement is not curtailed in order to achieve a constant surface speed. Your spindle speed is varied. So in order to use CSS, you must have the ability to control your spindle from Mach 3, be it with a PWM or a step direction frequency converter. As you change your spindle speed, you can see that our CSS increases. If at 100 RPM we remove 18 linear meters per minute, at 200 RPM we would remove 36 linear meters per minute. And again, as we move inward with our X, the amount of material removed per minute would be less. I suspect those of you who wish to use constant surface speed already understand the concepts involved, so we won't go too deeply into that either. So if we go back to the cycle screen, just so that we know what else is on here, that's pretty much it. This is the only screen, however, that you have a button called Cycle Start, which will start cutting your program. All the other screens are simply ways to set up and load programs. But this screen here, although you do have an edit button and can edit a program on the fly just in case you want to, this is the only place that you have a cycle start button to actually start a program. You can also control your spindle on off, coolant on off, stop a program, go into single movement mode, or rewind a program. You can also run a program from here if you click into the display and scroll down to a particular position and hit from here. You can see that you get the same warnings that you will in Mill, which is telling you press cycle start for a preparation move, and turn on the spindle if it's appropriate for this particular routine that you're doing. In this case, I would turn on my spindle and then hit cycle start. The program then will tell us it's going to make a preparational move to the beginning of this line of the program, at which point it makes the move and we're ready to go. You'll notice in this case I have the spindle on, but I have no spindle true RPM reading. That's because I don't have the machine hooked up at the moment to it, and I'm not feeding a spindle pulse into the machine. Tools are selected. I'm going to stop this. Tools are selected in Mach 3 with MDI lines or by typing into a tool selector. Normally, however, you will select them with an MDI line or in G-code, of course. T01 would mean tool 1, and the following two numbers would mean offset number 1. It is possible to select offsets from other tool entries using any tool. So you could, for example, type T0105, which means use the offset from tool number 5, but use the other dimensions of tool number 1. That's an advanced usage, however, and for most new beginning users, and who else will be watching this video, you'll be using normally T0101 or T0202. So you're basically going to be duplicating the first two numbers on the second two numbers. Now, we've gone through how to set up to the stock by jogging in, taking a skim, measuring this distance and entering it into the XDRO and hitting part 0. But how about a tool table? Well, if we quit mode and look at the tool table, you'll see we have a touch button. You can, on the other screens, if we were on our manual screens and we moved into the piece and we jogged in so that a tool, any particular tool, is touching our diameter, and we know, because we've already set the diameter as 14 in this case, to adjust tool lengths, you only need to jog in to touch the tool, return to your tool table page, and hit touch. Whatever tool is currently selected will now be zeroed in its X and Z length to be equal to that position. You can fill a tool table this way simply by selecting tool after tool and zeroing it with the touch position. The tool table will remember these values and will keep them in mind next time you start the program. Hitting touch when you're not sure whether you're zeroed will simply invalidate that tool because the numbers that are entered will be wrong. You can, for the sake of convenience, change your icons to make them look like your particular cutting tool types look. You have a tip direction, a tip radius. These two values are used in tooltip compensation, which will be a separate video. It is an advanced feature of lathes, and it allows you to cut profiles without worrying about which direction your tip faces and so on, messing up the job. The information in tooltip direction and tooltip radius are important to the program so that it knows how to correctly offset the distances that it's moving in a G-code program to compensate for that tool's direction and where it's pointing. The X offset and Z offset are simply the length of your tool and the distance from side to side of your tool as they differ from tool to tool. These are automatically set for you when you hit Touch Tool. X wear and Z wear are numbers that, if you have a valid tool table, you can increase or decrease these numbers when you notice that a tool is slightly out of tolerance due to wear or other factors. Normally, you'll increase these values as a tool wears. So you're basically saying, I'm happy with the settings of this tool. However, I have found that it has worn down by a tenth of an inch. And at this point, that tenth of an inch will be used to compensate the length of the X offset. You also have one for the Z. The turret position is used for those who write macros, which can automatically switch tools using a rotational tool turret. They can grab information for their macros from this table, telling them whether or not the angle that they're currently at is appropriate, and then using a macro to adjust that angle. For tool post, we could select it as front or rear. The only thing that this does is switch from the G54 to the G55 offset system so that a rear tool can automatically be changed in its X dimension and its Z dimension so that the program knows that the same coordinate system it's using will be appropriate for a front or a rear tool post. If you use a rear tool post, you must at least make sure that your tool table is valid for it by using your part zeroing command on a rear tool at some point. That's pretty much it for turn in terms of an introduction and showing you which buttons do what and where to go from there. More videos will follow on the turn series as time goes by, and we'll show you more interesting things that you can do. But this video is really meant to get you started in turn and show you what you need as far as screen controls to cut turn jobs.